Okay. Um, Good evening, everybody. Thank you for turning out. Um, this weekend is a public holiday weekend in the UK, so I guess a number of people are going to be away. The observant amongst you will have seen that there are two Paul Hearns. I'm hosting tonight because the real Paul Hearn didn't think he would have a sound Ethernet connection, but it turns out that even rural farms in Devon now have the internet, apparently. Um, Welcome to our speaker. Good evening, Alex. Alex is a PhD student, hopefully not for too much longer, because I believe he's submitting this month. So good luck. I hope it all works out for you. If it hasn't worked out by now, it's too late. So good luck with your submission. We're going to speak about machine learning and Zooniverse. And I think machine learning is something that is a huge buzzword now. Everybody's heard of it, everybody's seen it, and there's even, I know from discussions, people who would like to use it in some things we do um, as amateurs for a hobby. So I'm looking forward to being greatly illuminated tonight. Um, Alex, the floor is yours.
Sure, thank you, and thank you very much for having me. It's really excited to talk to everyone. Yeah, and as you say, I'm in fact I'm submitting my thesis next week, so I'm a final week PhD student. So yeah, that should go well, I hope. Yeah, so I'll share my screen. It says that the host has disabled this participant screen sharing at the moment, so I'm not able to do that yet. Now I can. Excellent, thank you. Um, okay, so hopefully everyone can see this. Um, yeah, so thank you for having me. I'm going to be talking to you about basically some of the work I've done during my PhD on finding interesting radio transients with some machine learning and citizen science and sort of interplay of humans and machines. Um, and so I'll sort of talk you through this. So I'm going to sort of hopefully convince you, if you're not already of this opinion, that radio telescopes are great, machines for doing interesting science, and then hopefully tell you that citizen science is amazing for doing science and also engaging with communities and engaging them in science. And I'm going to talk a little bit on anomaly detection. That's the specific sort of machine learning stuff I've been working on is anomaly detection and certain algorithms that we use to find weird things in the data. So to begin with, the telescope I use is this one here. So this is the Meerkat telescope in the Karoo region of South Africa. So you can see this sort of dusty scrubland that stretches out for many kilometers. So this is a good place for a radio telescope because it's far away from um, basically anyone, and there's very low population density, so you don't have too much RFI from humans. And there are 64 of the Meerkat dishes out in the desert here, each about 15 meters in size. We can see a sort of, and then a sort of offset Gregorian dish you can see on the side there. So this is the telescope I use, and the reason it's called Meerkat is originally there were 7 of them, which they referred to as the Karoo Array telescopes. That's the cat, and there was 7 of them, and then they sort of built more, and the Afrikaans word for more is meer, and so it's more of the Karoo Array telescope. And I'm sure it has no, it's completely coincidental that that matches with a small furry animal which is found in that area of the world. I'm sure that's complete coincidence. Um, so Meerkat is a fantastic radio telescope. It's really sensitive. It gets to sort of pretty unrivaled sensitivities in relatively short observations. And for its size, it has a pretty wide field of view. So what you're seeing in the background here is sort of roughly one sort of pointing with Meerkat, which gets you something like twice the full moon on the sky, so about a square degree or a bit over that. And its sort of main observing frequency of about 1.3 gigahertz. It's got receivers that go up to about 3 gigahertz, an S-band receiver and a UHF receiver at slightly lower frequencies. But I've mostly been using the L-band around 1.3. So you can see this lovely sort of picture of all these amazing dots on the right here. This is the kind of thing you get with a really long observation with Meerkat. And basically, if you take very sensitive pictures with a relatively wide field of view, very regularly, then you're sure to catch interesting things changing in the sky. And that's kind of what I'm interested in finding. What I'm going to play for you briefly here is some of the data or sort of pointings of some of the data I've used. So every time you see these blue dots flash, is basically as part of the survey team I'm a part of, is when we were looking at that little patch of sky and sort of overlaid on a low frequency sort of map of the galactic plane. So you can see the galactic plane goes through the middle of this picture, and all of these sort of dots, like how frequently we go to those different parts of the sky. And I was just using this to illustrate the point that with the survey team I'm part of, which is called the Thundercat survey, we sort of regularly visit all these spots in the galactic plane, and I use those to find interesting things that are sort of going bump in the night. And I could let this play, but we've got 5 years worth of data, so I probably won't let it run for 5 years. But each of these dots, these sort of numbers next to them, 1743 or 329 or whatever, these actually refer to, most of these observations are taken pointed at particular sources. And that was sort of at the center of each image, but there's a lot of other stuff we can do as well. So this is sort of illustrating that idea. So on the right here is a picture taken with Meerkat. This is about an hour long integration with Meerkat. And in the middle, you see this sort of earlobe shaped thing. I suppose if I'd been the one to discover this, I probably would have called it the Earlobe Nebula. I don't think we get to call things that anymore. But in the middle of this sort of Earlobe Nebula here is a system called Circinus X1. And Circinus X1 is a neutron star X-ray binary, which is very interesting. But every time we take a picture of it, you also get all this other stuff sort of for free every time you take a picture. So there's interesting sort of remnants of supernova that have exploded many thousands of years ago, and sort of regions of star formation in our galaxy. Down in the bottom left here, you can just about make it out. There's a extragalactic source there. So that's a radio galaxy many megaparsecs away, and lots of little dots as well of compact objects that might be interesting. And so my sort of work is all about this idea of doing commensal studies. And commensalism is originally a sort of biological term, a sort of ecological thing where you have a sort of a shark that does its own thing, and then a filter fish that sort of feeds on the scales of that shark. But in an astronomer's world, that really means there's a big fish PI who takes lots of data, and then I, as a PhD student, get to use it for my own aims as well. So this has been quite fun. And so what this means is all of these observations were taken, for these other science purposes, and I've been able to use them for my own with 0 additional hours of telescope time. So this is the kind of stuff we get for free. In a sense, which is really great. So the kind of things I'm sort of interested in finding are things that are varying over time. And I'm just going to talk you through a few kinds of things we might be looking for. So our nearby sort of stellar neighbors can show some really interesting activity levels. So this sort of GIF in the bottom right, you can see this. Hopefully, you can see this thing that's sort of popping in and out of the picture. So this is a nearby flaring star that we caught with Meerkat a few years ago, and we see it's not there for most of the pictures, and then it appears quite brightly and then disappears again. And so what we think this is sort of somewhat similar to our sun, but probably more actively so, is something like in the top right here, where we have these sort of prominences and bursts that come off of these stars and produce radio emission that we see with our radio telescopes. Also, sort of, I've already mentioned X-ray binaries very briefly, but X-ray binaries are sort of what you can see in this sort of schematic on the bottom left here, where you have normally a black hole or a neutron star and some unfortunate companion whose matter gets sort of accreted onto that black hole, and they shoot out these sort of jets that you can see in this cartoon here. And these two sort of panels on the right are when these sort of jets get shot out, they sort of it's like a sort of cannonball, basically. They sort of shoot out big blobs of plasma that are very, very fast. They're moving at sort of speeds approaching the speed of light. And what you can see in this GIF that's loading here, you can see these sort of blobs slowly moving to the north and south, and this will get brighter and fainter. These are actual blobs of plasma that are spat out from near this black hole at speeds approaching the speed of light. So this is something like maybe something like the mass of the moon traveling through space at nearly the speed of light. So these are very, very cool and very extreme systems that we can see in our galaxy. Stepping outside of our galaxy, the kind of things that we might see varying are supernova. So perhaps people are familiar with these. So when massive stars die, they sort of collapse and explode, producing these amazing sort of bright things and you can see in this picture here, they can often sort of regularly outshine their host galaxies. And on the left here is a picture of the Crab Nebula, which we see in our own galaxy. And we know from records from Chinese astronomers that the Crab Nebula was formed 1,000 years ago when the supernova blew up. And today we still see at the core of this supernova, we see a rapidly rotating neutron star that's sort of the leftover remnant of that supernova. So they're very interesting as well. I've got a couple more things. So this, what I'm showing you here is what's known as a tidal disruption event. So this is again a black hole in the middle of a galaxy, and if there's some unlucky star is unfortunate enough to wander too close to that black hole, it sort of gets shredded apart. And again, you get this sort of disk of material that forms around it, and these sort of jets that sort of spew out either side. And these can be very extreme, and we see these across the universe too. So hopefully, I'll probably hopefully that gives the point that there's lots and lots of stuff to find. But the problem is we have perhaps too much to work with. We have many thousands of images covering huge patches of sky, and far more than a single PhD student can look through during a PhD, basically. So the one solution to dealing with this when we have too much data and not enough eyes is citizen science. So I've spent a large chunk of my PhD working on citizen science projects on the Zooniverse website. So the Zooniverse website is exactly this, a sort of host for public-facing science and volunteer engagement. So there have been many Zooniverse projects. Perhaps people here might have heard of things like Galaxy Zoo before. And so far, the Zooniverse has had over 2.5 million people contribute 750 million classifications. So it's a real shining success in engaging people in science and getting some really cool results in astronomy and beyond, in fact. Yeah. So if you go to the Zooniverse website and go on the space section of that, you'll be greeted with something like this, where you see a sort of array of projects. And I'm going to be telling you about my project in a second, but if basically if anything in astronomy takes your fancy, there's probably a Zooniverse project related to it. So if you like finding planets, we've got planet finding things. If you like looking at the aurora, we've got stuff classifying aurora. If you want to find interesting galaxies have been running for almost 20 years now, actually, which is quite impressive. There's interesting stuff on interesting stars. There's stuff on gravitational waves, all sorts of interesting things here. But I'm going to be telling you about my citizen science project. So in my PhD, I've launched my own project on the Zooniverse called Bursts from Space and Meerkat, because I'm interested in finding these interesting bursts from space with meerkat. So in our first data release, we had about 9,000 things that we showed to our volunteers. What we showed them is what you can see on the right here. So on the upper panel is a light curve. So this is just over time, how does the brightness of the thing in your picture change? You can see that this is an example of something that stays fairly steady and then gets much brighter and then fainter and then brighter and fainter again. We showed them that, and then we showed them a sort of postage stamp sort of cutout of where that source was in the sky. And you can see it's just sort of a dot in this case. And these dots are the kind of things I'm looking for. We're looking for things that are dots that are varying over time, because these could be very interesting compact objects or stars or so on. And on the right here, you can see here are the things that people can sort of classify things as. It's very simple sort of workflow where we just say, what kind of thing do you see here? Does it look like a stable source? By which I mean, it's just sort of there's no variability. The light curve is not getting brighter or fainter. Is it some kind of extended blob in this picture here? Sometimes we see extended blobs in the form of distant radio galaxies, or as I showed you earlier, sort of nebulae or supernova remnants in the Milky Way. We sometimes, fairly rarely, but sometimes get imaging artifacts as a result of the imaging process of the radio data, and those can be a bit spurious and annoying, so we don't want to keep those. Or is it an interesting transient variable? That's sort of what we want to find at the end of the day. We show them sort of stuff like this. So you can see, for example, on the left here, it's sort of a relatively flat light curve. It's going up and down a little bit, but you can see there's quite large sort of error bars on each of these measurements of the brightness of that source. Whereas the thing on the right is clearly there, and then it disappears and then comes back again. So this is the kind of thing that we do want to find on the right. And that's another example of well, so we did this in partway through my PhD, and I set up uploaded about 9,000 things for people to look at, and we got about 89,000 classifications in 3 months, which levels out to about a click a minute for the whole 90 days, which is really amazing. We had over 1,000 volunteers take part. And what you can see on the right here is a histogram of how many people voted for how many things. So you can see sort of most people do very few votes, and that's completely understandable. And then sort of a few people do many votes, and then, individual volunteers doing 40, 60, 75, 95% of the sample that they're voting for. So it's amazing that there's people engaging with many thousands of things that we've shown them, which is fantastic. So the sort of median number of classifications is about 80. So it's amazing that people are engaging 80 times with our project. And I said that we had 9,000 things people to see, but we have 89,000 classifications. And that's because we take 10 classifications per thing and use that to sort of aggregate over their results. So what I did was then take everything that where 4 out of 10 or more of our volunteers said something was an interesting variable thing in the sky. And I sort of looked through all of those, and that provided a final list of 168 variables and transients that our citizen scientists found. So this is perhaps a little bit over-egging it, but thought I'd show this up. This is a way I like to show sort of how volunteers can find things that we wouldn't have found otherwise. So what I'm showing you on the right here is a slightly complicated plot, but basically these two axes are two statistics that were traditionally used for finding these interesting transients in variables. And the bottom line is basically that most of the things our volunteers found, which are these sort of blue points you can sort of see scattered amongst this cloud, most of them are not discrepant or extremal in their values using these two statistics. So a few of them are, that's these ones here, and these are mostly the things we pointed the telescope at that we were looking at for these interesting X-ray binaries. But all these ones down here, all these blue points, if you use these two statistics and trying to find the ones that are, the most different to everything else, you wouldn't have found these basically. So our volunteers are able to find things that we wouldn't have found otherwise, which is, really a real sort of shining success. But back to the sort of the actual things that they found, I thought I'd give a couple of nice examples. So I'll start with one that's in our galaxy. So what I'm showing you here, so here's the light curve that our volunteers got. You can see there's sort of nothing in the first 4 pictures of this part of sky, and then this sort of very weirdly structured and variable light curve you can see here. And what I did is I took this data and then thought, okay, well, what else has looked in that part of the sky and what did they find? So on the bottom left panel here, this is an optical image of that part of sky, and you basically don't see anything. There's sort of nothing at that location. But if you look with a sort of far infrared telescope, then this is what you get here. You get this really clear, bright signal coming from exactly where we were looking. So really, really stonkingly bright. And so what this source is a star that's lived through its main sequence, lived through its main life, and is now sort of in the end stages of turning from a star into a sort of gaseous nebula. And that sort of nebula emission, the sort of wind that it sort of outgasses, is sort of shrouding it from our view. That's why you can't see it in the optical, but the infrared light can shine through that, and so you see this really bright star in the bottom right. And this sort of dusty environment around this star has molecules in it. It has OH molecules in it, hydroxyl. And the sort of light that sort of shines into that cloud sort of creates a sort of laser-like condition where the molecule sort of gets excited and then de-excites, and we see that emission in the radio light curve at the top here. So this is quite an interesting thing to have found. We don't see that many of these things being variable and perhaps not on these timescales. So this is an interesting sort of result of a sort of probing the densities of environments of massive stars is it's quite interesting. And here's one that I really personally like myself quite a lot. So here's the light curve that our volunteers saw on the right. So again, you see this very variable thing where you can very clearly see it going up and down and up again. Our volunteers voted for this as clearly being an interesting variable thing. But there's no other counterpart at any other wavelength. If I look with an optical telescope, if I look with an infrared telescope, an X-ray telescope even, we don't see anything at this position. So, who knows what this kind of thing is? We still actually don't know. But I really like this one because one of our volunteers commented saying, this variable is so perfect that they raked through the metadata to see if it was a simulation, because some projects toss in sort of test examples to sort of test participants, and said this is so crazy that this is real. It's just too perfect. Bravo, space. So maybe, if you don't take away anything else, just Bravo space is a nice sort of message to sort of take home, isn't it? So we found all sorts of interesting things with our volunteers. And yeah, so this, in short, this was a really fun and a successful part of the PhD. So we published a paper on this just over a year ago now. And all of this data is sort of accessible. So if for the community to find interesting things and go and follow up on these things our volunteers found. And so this is the author list I'm just showing you here. So the first 21 or so are professional co-authors, and then the following 23 or 4 are the volunteers who helped us do some of the classifications of those sources, which is so it's really good to give them the credit, because after all, they're the ones finding these things. And I will, maybe the eagle-eyed amongst you will have spotted that the first of the volunteers shares my last name. And in fact, that is my dad. I showed him the Citizen Science Project, and he loved it so much that he did 1,500 classifications, and found one of the things that I showed on the previous slide. So he gets credit. So it's nice that my dad's on the paper with me. It was a personal touch. So that went really well, and so we thought we should do some more of this. So I've taken some other data. You can sort of see one of the bits of data here on the right here, from a different survey, still with Meerkat, of this field, and we sort of wanted to see if volunteers could find interesting things in this data as well. And again, you can see all these millions and millions of dots here could be very interesting things. We also thought, well, citizen science is a great tool for engagement as well. So how can we sort of engage in communities and sort of develop our outreach capacity with this as well? So this sort of materialized as a sort of workshop session that we ran in South Africa. So I'm showing you on a map here where Meerkat is in South Africa. So you can see this sort of blue square sort of in the top middle here. That's where Meerkat is itself. The nearest town is this one here called Carnarvon. I say nearest, it's about a 2-hour drive. So actually, things are quite sparse up there. And then most of the headquarters for Meerkat is actually down in Cape Town, down on the bottom left here. So South Africa's National Science Week was in late July last year. And so we ran a sort of project with students from the high school in Carnarvon. Students is about 15, and they're all sort of at the stage in their school careers where they're making decisions about choosing science and maths going forward in their education. So this is a nice time to sort of engage with them and see what they think of doing astronomy. So here's a zoom in of that part of the world. So again, Meerkat on the top left here, and Carnarvon on the bottom right. Oh, an hour and a half, right, there you go. And I was lucky enough to get to visit. So here's a picture of me with Meerkat in the background. We actually couldn't take pictures any closer because they were worried that the electronics in the camera would be too loud for the receivers. So we couldn't take the camera any closer. But I promise you it's there in the background. And as you get a sense, this is a very rural part of the world. This is very sort of sparse. And the telescope operator team, SKA, so that's the South African Radio Astronomy Observatory, provide a large fraction of employment in the town, and so they're sort of big force for change there and sort of developing things in the community. And in general, it's a fairly sort of underserved community. There's a school of, if I remember rightly, something like 500 students with really quite limited access to science. So we thought this would be a great place where we can sort of show them what cool science they can do and engage with the Citizen Science Project. So we took these students, these 15-year-olds, down to Cape Town for a few days to learn about astronomy and then do some of the Citizen Science Project. So on the right here, you can see this is the operations room in Cape Town, where the students are sort of learning about how the operations are done with Meerkat, how they do the observations and so on. And then they took part in the Citizen Science Project as well, and they sort of asked me about the kind of things we were after, and they did some of the classifications using the workflow I showed you earlier. And this was really great. It was sort of a great way to give these students sort of direct access to the facility that's kind of on their proverbial doorstep, right? This is it. I mean, Meerkat is a world-class telescope. It's the most sensitive interferometer in the Southern Hemisphere. And here are the students who live in the next door town who get to access that data and sort of find science with it, which is great. And then we also got them to talk to some undergraduate and master students in Cape Town to talk about sort of their career plans as well. So sort of developing that sort of impact over time. We also got to do a bit of history with them as well. So on the right here in the back, you can see some of the historic domes of the South African Astronomical Observatory, which has been by the Cape of Good Hope for about 200 years now. So this is sort of the a chance to see some of the history of doing astronomy in the Southern Hemisphere and show them around this as well. So that was a nice thing for them to do. Um, so we're sort of when working with these people who are based in the Northern Cape, there's quite a lot of indigenous knowledge of the area, sort of going back to for quite a long time. The original inhabitants of this area of the world, the Sand people, they've been there for 70,000 years, and there's amazing rock art you can find around the desert, sort of in Karoo and into the Kalahari, and there are sort of existing ongoing surveys to preserve that sort of knowledge of both the land, but also their sort of their understanding of the cosmos, sort of their creation myths, their constellations, this kind of thing, and how that sort of links to them on the land. So this is kind of a nice way to sort of keep that all recorded. As a final note on this, we also had some help with from the International Astronomical Union to help translate this project. So the stuff I've shown you so far has all been in English, but in South Africa there are about 12 official spoken languages. So on the right here is sort of a map of some of these spoken languages. So so this red one here, I think, is Xhosa, or this blue is Zulu, for example. I think the green will be Afrikaans, for example. But we had some help from the IU to translate this into these national languages of South Africa. So that's great. So people can do science from all across the world, and the people from this part of the world can do it, in their mother tongues. So that's a sort of, really nice thing to be able to do. And this went really well. So all this sort of engagement we worked on went really well. So what I'm showing you on the bottom here is basically how many clicks we had per day when we launched the second data release. And you can basically see that every sort of uptick in votes corresponds to when we did things with this engagement work, I had a couple of interviews and talks I gave, or I was on a couple of podcasts to discuss this. So you can see that this sort of chunk here, these 3 days here with the students themselves, they did about 3,000 classifications, and then I was over the next couple of weeks, I was on a couple of podcasts that you see sort of shot up the classifications by quite a lot. So if you share the news, then people will come, which is really great. So that was all really successful, and there's more results to come on that in due course. The first data release took 90 days, like I mentioned that already. This second data release took about 4 months, a bit longer. And what I'm showing you on the right here is basically some of the state-of-the-art, most sensitive observations of the sky with Meerkat. And doing anything to this kind of depth over large patches of the sky would take a lot of time. It would take an order of magnitude more time, so we would need an order of magnitude more volunteers to do it sort of at the same rate. So we're starting to run into problems of this being, this is not infinitely scalable for really deep imaging over large patches of the sky. So you're thinking, oh, how can we sort of scale this result? How can we use what the volunteers have done to sort of inform that going forwards? Which maybe some of you can see, this is where machine learning comes in. So we have lots of data. We have labels from our volunteers. This is sort of a prime recipe for doing machine learning. I've mostly been doing it with a package called Astronomy, which is the logo on the left here. So mostly what I've been doing is unsupervised machine learning. So this is where the machines don't train on what the volunteers have said. They sort of form their own way of thinking about the data. And then I'm going to compare that to what the volunteers said and see where do the machines and the humans agree, where do they disagree, and what can we find. And that way, if the machines agree with what the humans say, then that's good, because the machines do it much quicker. So maybe that can be a way of getting through large piles of data very quickly, or they're not matched, for example. So the first step of doing machine learning, you have to sort of describe your data in some way, in a sort of more concrete way than just sort of showing these pictures. So I do this with a couple of sort of packages that sort of describe my light curves. You can sort of think of these as measurements on the data. So maybe, for this thing on the left, maybe the amplitude of it, or the width of it, or sort of the gradient of the points on this line, maybe. And we can use those to describe our data. And there's a sort of second way of describing our data that I use that's a bit more abstract, but you can show that you can basically break any sort of time series signal like this into a set of functions that have some sort of wave-like shape, with some sort of amplitude attached to it. And so we use these sort of wavelets that you can like see on the bottom right here, this sort of wave-like sort of pulse. And we sort of use a set of these to describe them, and then we can take those amplitudes and use those as descriptors as well. This is all a bit technical, but point is we have lots of numbers that describe our data, and this is kind of what those numbers look like. Now, this is really, really getting abstract now. So this is when you use those numbers to describe our data, and then trying to plot it in 2D, then this is what it looks like. But we have 45 numbers for every bit of data, and I can't really picture 45 dimensional space, so we've sort of collapsed it down to 2D. And most of this is just to show you sort of see in the different patches of sky that we targeted, we get this sort of interesting substructure in this. And the aim of the game here is really just that all these things that have stars on, so there's some orange stars here, there's some purple stars here. These are all the transient things that our volunteers found. And so we sort of want to see if the machines can find those without the volunteers telling them. And then that means we can sort of do more going forwards. So the aim of the game is we want these stars to be sort of separated out from everything else in this kind of diagram. The actual sort of anomaly detection that we do, this is the actual core of the machine learning, is done with these two algorithms, one of which is called a local outlier factor, and one of which is called an isolation forest. And I'll spare you the gory technical details, but basically both of these things have ways of internally defining whether something is an anomalous or normal in some capacity. So, for example, on the left here, if one thing is very different to everything else, it's probably an anomaly. And if it's very far in some data space, then it's probably an anomaly. Whereas an isolation forest is a sort of tree-based method. So you can imagine if each of these branches is separating data A from data B, then you sort of split them all up, and you can sort of use properties of how these trees split things to decide how weird and wonderful some of your data is. So yeah, there's technical details, but the long and the short of it is that both of these sort of models calculate how anomalous everything is in your data and they return to me a list of my objects from the weirdest to the most normal. So from the most anomalous to the least anomalous. And the sort of the punchline is kind of this. So in that list where we have going from the most anomalous things to the least anomalous things, and that's going along the x-axis on this graph here. We want to see where do the things that our volunteers found interesting, where do those things fall? How quickly do the machines find them, basically? And so all these different lines are showing basically combinations of different ways of describing the data and using different models, how quickly those things are recovered. I'll just draw your attention to two of these lines. So this one here on the left goes through about 50% on the y-axis and 10% on the bottom. So this says that you can find half of our interesting things that our volunteers said were interesting in 10% of the data. And then this other one here, it says you can get 90% of the things our volunteers found were interesting in 30% of the data. So basically this says you could chuck away 70% of the data and you would still find 90% of the stuff relatively quickly. So this is great. So we can already cut down the amount of data we have to deal with by 70% and still keep 90% of what we were looking for. And this stuff runs really quickly. I ran this on my desktop and it did it in 10 minutes. So that saves our volunteers having to look through months and months worth of data and finding good chunks of what they were after. There's one final little sort of addition to this is that there's no guarantee that the things that the algorithms thought were weird are the same as the things that I think are interesting. They might find something very anomalous, but it might be something instrumental. It might be something I'm not interested in. So there's a sort of machine learning paradigm referred to as active learning, where I take the data and I sort of it sort of forms a recommendation system. Maybe you're familiar with on Netflix. If you watch something, then Netflix will sort of recommend you things that are similar to that. This is sort of similar. So I'll sort of go through the data with this user interface on the right here, and I can vote for things and say, oh yeah, get this one's 5 out of 5. Show me more of those. Or this one's 0 out of 5. Show me less of those. And so it sort of forms a recommendation engine by doing this. It sort of queries just a small subsection of the data and then learns, what my my preference is. So what it should show me more preferentially. And we can see how that improves our recovery of these interesting things. Um, and this is a sort of slightly busy diagram to show that. I'll just focus on these two sort of most obvious lines you can see sticking out the top here. So basically, these gives the y-axis is how much better this active learning does than the sort of defaults. And in these cases, we can get up to 10% better really quickly. So by doing this fairly simple sort of show me more of this and show me less of that, we can do over 10% better, which is a really good sign. So that's sort of the main things I sort of wanted to chat to you all, and say that citizen science is a great tool, both for finding interesting things, and I've given you a couple of things that we found, but also with engaging with communities and spreading the joy of doing cool science. And then I've talked a bit about machine learning, uh, and the anomaly detection I've done, and this is going to be really important moving forward. So um, I'll leave it there and take any questions.
Okay, are there any questions for Alex? Don't be shy, just unmute yourself and shout.
Well, I've just noticed something. Carnarvon, not very far away from Meerkat.
Mm.
If you go to Western Australia, you've got another Carnarvon, not very far away from SKA.
I didn't know there was a Carnarvon in Western Australia.
And
Oh,
the only anomaly that I can see now is that we don't have any radio facilities near Carnarvon in Wales, but we should have.
yes. I mean, the only telescope that would do any good in Wales is one that you can get through the clouds. Yeah.
And Carnarvon in Western Australia has been a space town for a long, long time because it used to be a NASA tracking station as well.
Oh, excellent. I didn't know that. That's a really
Yeah.
nice history. Yeah. Yeah. So I mean, so Meerkat is sort of part and parcel of some of the SKA development. So some of the, part of the SKA is going to be in Western Australia, as you say, and then some of it is also going to be based around Meerkat there. So that's quite a nice twinning there. I like that. Yeah. Excellent.
Alex, I was very interested in the connection with the high school in Carnarvon.
Yeah.
And was that a part of the initial proposal for Meerkat when the funding was raised? Or is that an element that your own project has brought?
Yeah. So I don't know absolutely all of the history, but certainly that they were already embedded in the community before I came to them with this stuff. They already had programs working with people from the school. They had they do some robotics projects with them as well. And as I say, they're sort of engaged in sort of employing people in the town and so on. So they were already sort of embedded in the community in that sense. And this was just another thing that we could sort of add to that story. And sort of more generally, Soreo, who run Meerkat, I don't know if this was part of the brief from day one, but certainly from very early on, they've always had an emphasis on what they refer to as human capacity development. So basically, 35 years ago, there were about 40 astronomers total in South Africa, and now they've got one of the biggest and best telescopes in the world, and many hundreds of astronomers. And so building up the homegrown talent there, including and especially representing the majority of the population and not historically basically white South Africans, developing that sort of and increasing the fraction of black South Africans who are astronomers and women who are astronomers has been a real emphasis for Soreo. So they've been really keen on that for a long time. They also run bursary schemes for PhD students and postdocs to sort of develop that skill there. So I don't know if it was from day one, but they've been, in my eyes, very successful at sort of growing the astronomy community there. It's been a real success. Yeah.
Can I take a question? Just to make sure I've sort of got a grasp of your machine learning process, that you set the machine loose on the data with no preset conditions, so it can go, and presumably the code below that is designed to seek anomalous things and identify them and then flag them. And then right at the end, you have a sort of five button classification that says, I'm really interested in this, I'm not really interested in that.
Yep.
Does it store the intermediate data so that somebody else could come along and say, I'm actually interested in something completely different and
Yeah.
get a completely different set of results
Yeah, that's
or
very true.
anomalies?
Yeah. So certainly, yeah, the sort of the first step of doing the sort of standard anomaly detection, yeah, that sort of runs and then saves the results. So that basically, saves a list of these things and says this is the weirdest, and then this is the second weirdest, and goes through that list. And as you say, none of that is, it doesn't see the volunteer data or any of that. That's all sort of, as you say, it has some way of just defining something as being anomalous, and then sort of preferentially votes for that. And then then I add the layer on top of the recommendation system, the active learning of show me more of this and show me less of that. But as you say, that could be completely different for someone else. So with the same data, a different scientist who's interested in different things, may vote differently and then get different results. With the test I've done, the difference between the sort of default and then the active learning, as I said, was a sort of maximum about 10% difference. So instead of recovering 50% of the things, we recover 60% of the things, for example, in the top 10% of the data. So there's sort of that, that is a good chunk of difference. You'd have to vote very, very differently to get the results to skew massively from that. But in general, yeah, you could have someone else vote differently and produce slightly different results. So it is a bit subjective, but that's kind of good because I mean, maybe an instrument scientist who's interested in sort of calibration errors in the radio data, might vote differently, and that they could use that to find something else out about how to calibrate Meerkat, for example. So there's certainly, benefit in, as a scientist, there is a subjectiveness to what I care about, and that can be sort of folded into that in a good way, I think. Yeah.
Yes, because I know Chris Lintot's thing about citizen science is it in the the first project, it turned up things that nobody had noticed because you're looking for what you're looking for.
Yes, no, precisely. Yeah, it's always good to leave room for the sort of unknown unknowns. Yes, and I don't know if I said this. So Chris is one of my PhD supervisors, so we've sort of chatted a lot about this over the past 3.5 years. Yeah.
Any more questions?
Yeah, yes, I've got one. You probably said it right at the beginning. How many areas do you look at, and how frequently do you go back to them?
Yes, I think no, it's right to ask. I don't think I put the specifics on it. So the server I'm part of, which is called Thundercat, typically observes every weekend, so once a week, and sort of how often they look in those bits of sky is sort of determined by, as I said, I was using this data for the other project, that's sort of my work, but they were pointing it mostly at these X-ray binaries for the interesting jets that they spew out. And so the sort of observing schedule was based on how active they were in the X-rays. So if after 2 months that source was no longer doing anything interesting in the X-rays, then we didn't follow it up with the radio. So we sort of, for some systems, we've got 5 years of data every week, and for others that they were doing something interesting for 2 weeks and then stopped. So we sort of stopped taking data. So it's sort of a bit variable in how often we visited each patch of sky. In the data that I sort of used for this, I used sort of 11 of our fields, as I'll call them, sort of bits of sky that we looked at. 11 different fields of sky, which is a total of 507 different observations, I think. Yeah.
Is this concept of using data that was taken sort of serendipitously as somebody else was doing other observations becoming quite an important part of astronomy?
Yeah, it's sort of there's some people who will say that if your telescope only achieves what you set out to achieve, then it hasn't done enough, which I think is quite a strong take, but that sort of that is leaning in that direction, as you say. So yeah, there are quite a lot of telescopes that have, certainly radio telescopes that have, because it's all digital data, it's all sort of basically Ethernet cables plugged together. You can sort of have a separate data stream that you can sort of plug off in a different direction and do something else with it. So Meerkat has so this is stuff I've done with sort of the imaging products that we've sort of made from Meerkat, but there are other projects. There's one called Meertrap, which is looking for interesting transients, but sort of on much faster timescales. So they take a sort of custom Ethernet cable and take a different subset of the data away, and search for really, really fast transients. So things, if people have heard of fast radio bursts, that's sort of what they're interested in finding. And again, because Meerkat, points all over the sky, they can sort of use that data for their own ends to great success. So yeah, I would say this sort of it's science you get kind of for free, like when you have to design a project and a pipeline and so on, which is difficult, but it's a good way of making, squeezing more science out of the observations. And I think that's a real boon. Yeah. And there are lots of examples of this. I mean, things like, in other wavelengths as well. So Euclid is a telescope that launched last year sometime and takes amazing high resolution pictures of galaxies, primarily for doing cosmological studies. But for example, people who care about the shapes of galaxies, like for Galaxy Zoo, they'll be able to use them for their science as well. And so it's sort of, if you could design a survey that served everyone's interests, then we'd all go home happy, right? So yeah, I certainly think that's a good thing to always consider going forward.
Thank you. Any more questions? It's all gone very, very quiet. So, Alex, thank you very much. That was very much appreciated.
Thanks. It's great to chat to everyone.
And come back when you're Dr. Anderson and tell us about your next project. And good luck over the next 2 or 3 months.
Fantastic. Thank you very much for having me. It's been great to chat to everyone.
One of the things about this group is we give the audience a chance to present things. I don't know whether I haven't had anything from anybody. If they want to present some interesting results or say a few words about upcoming observing their planning, things going on in their local area. I usually get notice in advance. So somebody's got their hand up. Richard. Can you hear me? Hello, Richard. You popped your hand up. I don't know whether you wanted to. Okay, that's just a thank you. Okay, thank you, Alex. I've seen that in the chat. Well, in that case, then.
I've just got one thing about next week, next month. Alex, do you know Professor Roger Dean at WITS?
I do. Yeah, I do. Yeah.
Okay, but Roger is with us next. We're back in South Africa next month.
Excellent.
And Roger Dean is the director of the Centre for Astrophysics at WITS University in Johannesburg. So, and he's talking about the square kilometre array. So that's something else to look forward to from the Southern Hemisphere.
Okay, well, thank you very much, everybody. I'll let you go and enjoy your evening. Thank you.
Good luck, Alex.
Thanks very much.
Thanks a lot.